Welcome to the Agile Software Engineering Deep Dive, the podcast where we unpack the ideas shaping modern software engineering. My name is Alessandro Guida, and I've spent most of my career building and leading software engineering teams across several industries. And today I want to talk about one of the most repeated, and in my view, most misleading sentences in the current discussion about generative AI. It is just a statistical machine, guessing the next most likely word. I hear this everywhere, from tech journalists, from bloggers, from business leaders, and sometimes even from people who should know better. And the frustrating part is that the sentence contains a small piece of truth. Yes, generative AI uses statistics. Yes, it produces output token by token. And yes, probability plays a role in selecting the next token. But that is not the whole story. In fact, it is mostly the last step of the story. In this episode, I want to explain what actually happens inside a generative AI model in a way that does not require a master's degree in computer science. We will look at tokens, neural network layers, inference, context, and why the final probability distribution is only meaningful because of everything that happens before it. Because generative AI is not a human mind, it is not a truth machine, but it is also not a simple autocomplete toy. And if we want to use these systems responsibly in software engineering, product development, project management, and leadership, we need better explanations than slogans. Probability is the final step. Deep contextual processing is what makes that step meaningful. Let's dive in.
So if you were to stand on a sidewalk and just watch a self-driving car navigate a busy city street, dodging pedestrians, stopping at red lights, yielding to cyclists, it would be technically true to say, well, that's just a machine turning a steering wheel.
I mean, yeah, technically true, but that description totally strips away the entire physical reality of what's actually happening. Like, it completely ignores the cameras, the LiDAR, the radar, and all those millions of split-second calculations happening under the hood that make the turning of that steering wheel actually mean something.
Right, exactly. And we do this exact same thing every single day when we talk about artificial intelligence. So our mission today for this deep dive is to completely dismantle one of those stubborn, repeated, and honestly misleading cliches in tech right now. And that is this idea that generative AI is, quote, just a statistical machine guessing the next most likely word.
Oh, it's a phrase you hear everywhere, right? From tech journalists to CEOs, even professors. It's basically become accepted wisdom at this point. And it really reduces a remarkably complex system to a caricature. It kind of gives you the impression that generative AI is little more than like a clever autocomplete on your smartphone.
Yeah, totally. And to help us tear this cliche apart, we are diving into a really fantastic piece of source material. We're looking at issue number 31 of the Agile Software Engineering newsletter, which is penned by Alessandro Guida.
It's such a great piece.
It really is. It's a brilliant exploration of modern R&D and engineering rigor. Now, obviously, we are going to cover a lot of ground today, but you absolutely need to check out the full article for the in-depth details. I highly, highly encourage you to subscribe to the newsletter and its companion podcast, the Agile Software Engineering Deep Dive, just to support this kind of rigorous, thoughtful analysis.
Yeah, it is a highly recommended read. Because, the real danger of this specific cliche is that it actively harms our ability to understand the true power of these systems. I mean, if we don't understand the underlying mechanisms, we can't possibly engineer around its flaws or, properly leverage what it can do. But to explain why the cliche is wrong, I guess we first have to admit what it gets right.
Okay, let's unpack this. Because the tricky thing about this phrase is that it does contain a tiny kernel of truth, just like the self-driving car tuning the steering wheel. What is the actual technical truth here?
Well, the technical truth is that large language models, or LLMs, do generate text step by step. At each step, the model produces a set of probabilities for possible next outputs.
Right.
So it looks at those probabilities, selects one, appends it to the sequence it has already generated, updates its context, and then just repeats the process.
Let's pause on the word output for a second, because the cliche specifically says it guesses the next word. And our source material points out a major misconception right there. AI does not think in dictionary words.
Oh, not at all. No, it operates on what we call tokens.
Okay, so if it's not a word, what exactly is a token? Because this feels like the foundational crack in that whole autocomplete theory.
Yeah, so a token is really just a fragment. I mean, it might be a single word occasionally, but it could also just be part of a word, a prefix, a suffix, a piece of punctuation, or even just a few letters. Like, if the AI is processing the word unbelievable, it might see un, believe, and able as three totally distinct tokens.
Hold on. If it's processing fragments like un and able, how does it know what those fragments actually mean? It doesn't have, like, a dictionary it's looking up, right?
Right. It relies on numerical vectors. And this is where the sheer scale of the engineering comes into play. You can think of it as a massive, high-dimensional mathematical map.
A map.
Yeah, a map. When a token enters the system, it is converted into a set of coordinates on this map. So fragments with similar conceptual meanings or grammatical functions are physically grouped closer together in that mathematical space.
Wow. So it isn't moving through language in neat little dictionary units the way a human writer might. It's navigating a structural, mathematical map of concepts.
Yes, exactly. The system operates entirely on these structured numerical representations. It isn't reading text at all, really. It is doing complex geometry with meaning.
That immediately makes it way more sophisticated than just guessing words.
Yeah.
But I want to clarify the timeline of this whole pipeline. Because when you say it produces a probability, at what point in the calculation does that actually happen?
That is the single most critical distinction in this entire deep dive. The probability distribution, the part where it calculates what token should actually come next, that is the very final step of the process.
Wait, the final step?
Yes. It is not the beginning.
Well, it isn't just looking at a massive frequency table from its training data and saying, well, the word peanut is usually followed by the word butter, so I'll print butter.
No, it is absolutely not asking what word usually comes next after this one. Instead, it is asking, given everything I have processed so far, the prompt, the instructions, the constraints, the tone, what continuation best fits the overall structure and intent of the current context.
This makes me think of, like, reading a complex detective novel. If I'm nearing the end of the book, I don't guess the identity of the killer just by looking at the most common word printed on the last page. I have to process the whole story.
Exactly.
I'm holding on to the clues from Chapter 2, the alibi from Chapter 10, the motive from Chapter 15, and all of that context filters down until the final conclusion is basically the only one that makes logical sense.
That analogy perfectly illustrates what we call attention mechanisms in these systems. What you are doing in your brain as you read that novel, holding on to early clues, prioritizing certain pieces of information over others, building an internal narrative, is conceptually really similar to how the AI weights different tokens across its entire context window.
Okay, let's look at the engine doing that weighting then. Since we established that the probability math happens at the very end, what exactly is happening in the middle? What is this massive neural network doing before it ever picks a token?
Well, the heart of a generative AI model is a deep stack of neural network layers. And we can kind of break them down into three broad stages to understand the mechanism. The early layers, the middle layers, and the deep layers.
Okay, what do the early ones do?
The early layers are essentially dealing with local structure. They process immediate syntax, token patterns, and the basic grammatical relationships between adjacent fragments.
Wait, so the early layers are basically just doing, like, advanced grammar checks. At what point does it actually know what the sentence means?
The transition to meaning starts happening as that data is passed up into the middle layers. Here, the network takes that grammatical foundation and begins to connect broader concepts. It identifies longer-range dependencies.
Like what?
For instance, if you used a pronoun in your prompt, the middle layers are where the system mathematically links that pronoun back to a noun you mentioned, say, 3 sentences ago.
Okay, so it's building a structural understanding of the prompt. Then what happens in the deep layers?
The deep layers are where broad abstractions emerge. The network basically stops looking at the syntax entirely and starts interpreting semantic intent, conceptual relationships, and multi-step constraints.
Wow.
Yeah, by the time the data reaches the end of this deep layer stack, the model is no longer operating on your raw text at all. It is operating on a highly refined internal representation of the entire context.
This brings up a major point from the article regarding how the model actually applies this internal representation. We have to separate two phases of an AI's life cycle, right? Training and inference. And I think a lot of people assume that when they type a prompt into a chatbot, the AI is learning from them in that exact moment.
Yeah, that is a very common misconception. During the training phase, the model is indeed learning patterns from vast oceans of data. It's adjusting billions of mathematical parameters so that it learns how to build those deep abstract layers we just talked about. But that phase is over by the time you use it.
So when I am typing prompts into the chat box, what is actually happening?
You are in the inference phase. During inference, the model is no longer learning. It is applying what it learned. And this is where the iterative process becomes really reasoning-like.
How so?
Well, when it generates part of an answer, that new text becomes part of the ongoing context. The entire updated context is processed through those deep neural layers all over again. It builds an updated internal representation of the sequence, generates the next token, and repeats the entire massive calculation for the next one.
It's constantly reevaluating the whole picture with every single step. But here is something that really threw me when I read the source material. The cliché literally says, guessing the most likely word. But the article points out that AI does not always pick the most likely next token.
Oh yeah. It rarely picks the absolute highest probability token every single time. Engineers use techniques called temperature, top sampling, and nucleus sampling. These mathematically force the model to sample from a broader set of plausible candidates.
Hold on. If the whole point of this massive, multi-layered mathematical calculation is to find the most accurate, highest probability continuation, why on earth would engineers deliberately program it to choose a less likely answer? That sounds like you're intentionally making the AI worse.
It does sound counterintuitive, I know. But if a model always selected the highest probability token, a process we call greedy decoding, the output would become mathematically rigid.
Rigid how?
It gets trapped in repetitive loops, becomes robotic and unnaturally predictable. Language itself is inherently varied, By introducing controlled mathematical variance, essentially rolling a weighted die among the top sensible choices, the outputs become dynamic and adaptable.
So the very phrase picks the most likely next word is technically false on its face in almost all real-world applications.
Completely false. It picks a plausible next token based on a massive, layered contextual representation.
Okay, we've talked about vectors, neural layers, and sampling techniques. But to really drive this home, to move from the theoretical mechanics to practical reality, we need to see the AI actually do something that proves it isn't just an autocomplete toy. And the source article has this phenomenal aptitude test example that perfectly cements why the autocomplete theory completely falls apart.
Yes. The XTAM car fuel consumption test. It is a brilliant demonstration of multimodal capability.
Now, for you listening, I am explicitly not going to read out all the math and step-by-step algebra here. Audio math is a quick way to put everyone to sleep. You really need to go read the full article to see the visual layout of this test because it's super easy to follow visually. But what I want to focus on is the sheer magnitude of the mechanism the AI had to utilize to solve it.
Right. The problem requires significant cognitive-like filtering. The author basically feeds an image into the AI. It's a complex, visual, multiple-choice question.
Right. And to get the answer, the AI has to look at the image and recognize that it contains a bar chart, a data table, and a text question. But here is the kicker. It has to realize the data table contains totally irrelevant information about car prices and deliberately ignore it.
Which is incredibly difficult for a simple pattern matching system.
Exactly. Then it has to zero in on a specific bar chart for a specific car model called XTAM under motorway driving conditions. It extracts a numerical value from that visual chart. Then it has to read the text prompt, realize it's been given a monthly mileage, multiply that by 12 to get an annual figure, take the number it pulled from the visual chart, perform a division equation, and finally output the correct multiple choice letter, which it does flawlessly.
And let's analyze why this thoroughly disproves the just guessing words concept. An autocomplete engine simply cannot do visual filtering. It cannot cross-reference a visual chart against a text prompt.
Yeah, that makes sense.
If it were just guessing words based on frequency, the presence of that decoy data table would completely derail it because those numbers and words would heavily skew the immediate statistical context.
Because the words in the decoy table are sitting right there on the page, heavily represented in the local data.
Exactly. The model did not arrive at the answer by asking what word comes next. It had to build an internal representation of the image, recognize the semantic intent of the question, isolate the relevant variables, perform the calculation, and then express that representation in human-readable tokens.
Right.
The output mechanism, printing option B, is just the final visible step. of a massive representational process.
That phrase, representational process, brings us to a huge philosophical question. If it is building internal webs of context, solving visual puzzles, and successfully filtering out red herrings, does it understand? Does it think like us? Here's where it gets really interesting. I want to draw your attention to a specific paragraph in our source material that compares AI to human reasoning. It is a really fascinating parallel.
Yeah, it requires navigating a very nuanced middle ground. Let's be clear up front about what the architecture is not. Current generative AI does not have human consciousness. It has no lived experience.
Right.
It feels no emotion, and it doesn't have true, physical, real-world grounding. Like, it doesn't know what a car is in the physical sense, or what the texture of a steering wheel feels like.
It's not a biological mind.
But at a highly abstract architectural level, the mechanics of how it processes a problem are remarkably parallel to how humans reason.
Break that parallel down for us. What does a human actually do when faced with a complex problem that mirrors this technology?
Well, think about your own cognitive process. You collect signals from the world around you. You combine those signals with your previous experience, which is essentially your personal training data. You interpret patterns, you evaluate different possibilities, and finally, you choose the conclusion that seems the most coherent.
Which is exactly what the neural layers are doing during the inference phase we talked about earlier.
Yes. Both humans and AI transform an input into an internal representation before producing an answer. Both rely on deeply ingrained patterns. Both evaluate possibilities.
Interesting.
The substrate is totally different. I mean, we use biological neurons steeped in emotion and physical perception, while the AI uses mathematical vectors and attention mechanisms. But the abstract architecture of synthesizing an answer from context has an undeniable similarity.
The article also points out a flaw that we both share as a result of this architecture, which I thought was incredibly illuminating. Both humans and AI can be wildly, confidently wrong when our internal representations are based on flawed assumptions, incomplete data, or just a disconnect from reality.
Right. When an AI hallucinates, it isn't randomly glitching. It's usually because its internal representation of your prompt mapped onto a flawed or contradictory pattern in its training data. And humans do the exact same thing when we jump to conclusions based on our own limited experiences or misunderstandings. The logic process basically worked, but the foundational data was bad.
So we've peered into the neural layers. We've seen how it uses vectors to navigate meaning. We've seen it filter out decoy data in a visual puzzle. And we've explored how its internal representations kind of mimic the architecture of reasoning. But let's bring this all down to practical application. Why does the language we use to describe this technology actually matter in the real world? Like, who really cares if a project manager calls it a statistical autocomplete machine?
Oh, it matters deeply in the field of software engineering and product development. The way we describe AI influences how we use it, how we trust it, and how we build systems around it. This requires rigorous engineering discipline, not catchy slogans.
Give us an example of how that specific slogan holds engineers back.
Well, if a software engineering team reduces an LLM to just guessing words, they're going to severely underestimate its capabilities. They might fail to appreciate that it can actually generate complex, functional code, adapt architectural design suggestions, or synthesize massive technical documents.
Yeah, that's a huge blind spot.
They leave incredible value on the table because they treat it like a simple toy rather than a powerful representational engine.
Right, because if you think it's just guessing the next word, you wouldn't trust it to help you debug a complex software pipeline.
Exactly. But the danger goes both ways. If you don't understand the mechanics of those layered internal representations, you might fail to understand why it hallucinates. You might blindly trust an output because it sounds syntactically confident, not realizing that its internal representation was built on flawed training data. You really have to respect the underlying mechanism to use the tool safely.
The author actually summarizes this reality into 3 core truths of generative AI. Number 1, AI is not a truth machine. It doesn't inherently know facts. It knows structural patterns. Number 2, AI is not a human mind. It lacks consciousness and real-world physical grounding. But number 3, and honestly the entire point of our deep dive today, it is definitely not a simple autocomplete toy.
It is a profound, pattern-based system with remarkable representational power. It can generate immense value, but it is limited by its training data. And if you are trying to navigate the modern tech landscape, you just have to hold all those technical truths in your head at once.
And if you are listening to this and thinking, I want to know more about those neural layers. I want to understand vectors better. I want to see how the architecture really flows. The article lists some phenomenal resources to continue your learning.
Yeah, the author provides a highly curated progression, moving from very accessible overviews to some deep technical mechanics.
Yeah, for a really solid, accessible start, there's the Google Machine Learning Crash Course on large language models, and it really breaks down tokens and how these systems scale beautifully. If you want something visual but a bit more technical, Jay Alamar's Illustrated Transformer is kind of legendary in the industry for showing how information actually flows through these attention mechanisms without totally overwhelming you with heavy algebra. And then for the truly brave,
Yes, for the brave, there is the foundational 2017 paper, Attention is All You Need by Vaswani and colleagues. It is heavily mathematical, but it is the literal bedrock of every modern LLM architecture we use today. It's basically the paper that proved you could use these attention mechanisms to build deep contextual understanding.
which goes right back to our detective novel analogy, how the system learns what parts of the prompt to pay attention to. So, as we wrap up this deep dive, I want to remind you of the core takeaway. Yes, generative AI is built on statistical learning. Yes, probability is involved. But the real power, the actual architectural achievement, lies in the deep, layered contextual representations that happen before the math ever spits out a probability. The probability is just the final visible keystroke of a massive cognitive-like calculation.
We really have to stop mistaking the final visible output mechanism for the entirety of the system.
Absolutely.
Yeah.
And once again, I cannot give a stronger recommendation to go read the full issue and subscribe to the Agile Software Engineering newsletter and its companion podcast. Alessandro Guida is putting out some of the most clear-eyed, rigorously engineered analysis in this space right now. And if you want to stay well-informed without the hype, you really do not want to miss it.
But before we let you go, I want to leave you with a final thought to ponder that kind of builds on everything we've discussed today. We established that both humans and AI rely on their training data to build internal representations of reality.
Right.
Humans rely on lived physical experience. Current AI models rely heavily on human-generated text and data. But right now, the internet is rapidly filling up with AI-generated text, AI-generated images, and AI code. Future models are increasingly going to be trained on the outputs of previous AIs.
Oh, wow, like a huge feedback loop.
Exactly. So the question is this. If an AI's internal representation of the world is eventually built entirely on the mathematical dreams and structural patterns of previous AIs, rather than grounded human reality, how will its reasoning-like behavior evolve? Will it develop an entirely alien logic structure, or will it just become a closed loop and echo chamber, amplifying our own past patterns forever?
That is a haunting and fascinating thought, and really makes you realize that when we look at these models, we aren't just looking at a machine turning a steering wheel. We're looking at a system navigating a vast, invisible landscape of our own collective knowledge. Thank you so much for joining us on this deep dive. We'll catch you next time.
Thank you for listening to the Agile Engineering Deep Dive podcast. If you found this episode valuable, feel free to share it with someone who might benefit, a colleague, your team, or your network. You can access all episodes by subscribing to the podcast and find their written counterparts in the Agile Software Engineering newsletter on LinkedIn. And if you have thoughts, ideas, or stories from your own engineering journey, I'd love to hear from you. Your input helps shape what we explore next. Thanks again for tuning in, and see you in the next episode.